Okay, so welcome to the angular velocity unit, day 1. We're going to start with some dimensional analysis. You guys have to be really solid on this if you want to be successful in this unit. So, find your handout that looks like this, and we're going to fill in this box up here in the corner first with some things that you guys need to have memorized before the test for this unit. So, 180 degrees is, as we all know, pi radians. So let's fill that in. 1 revolution we know to be 360 degrees. It's 1 full revolution around a circle. In radians, that is 2 pi radians. 360 degrees is 2 pi radians. Okay, other things. 1 mile, 5,280 feet. You have to have that memorized for the test. I won't tell you on the day of the test. 1 kilometer is 1,000 meters. And then 1 meter is 100 centimeters. So a few things that you want to know in order to easily convert between units. So let's do a couple of examples, and then we'll move on to the other handout for angular velocity. So take a look at number 2. We want to convert radians to degrees. We have the equation for that, so we might as well use it. We're going to start with 6.2 radians. And we know that we have to multiply by 180 degrees over pi radians in order to cancel the units out. So I'm writing everything so we can physically see the cancellation of the units there. Okay, and then grab your calculator and let's do this. This is going to become 1,116 degrees over pi. Okay, 1,116 over pi degrees. So make sure you have that degree symbol there so I know that you're in the right units, but that's our final answer. Okay. When you guys are doing problems like this, I expect to see all of the work shown. So you want to show the cancellation of the units as well if you want to get full credit on these assignments. All right, let's do a couple more. Number 6. You guys find number 6. We want to convert 3.4 revolutions in 10 seconds to degrees per minute. So I'm going to rewrite this, and hopefully it looks a little bit more clear. So 3.4 revolutions in 10 seconds, I can rewrite as a fraction, 3.4 revs over 10 seconds. And I want to convert those into degrees per minute. So we've got to convert two things. The first thing we have to think about converting is revolutions to degrees. Okay, so that's one conversion that we have to make. We have to turn revolutions into degrees. Now, how do we turn revolutions into degrees? Well, we have this conversion up here. 1 revolution is 360 degrees. So that's something to note. 1 rev is 360 degrees. We're going to use that. The other thing that we have to worry about converting is seconds into minutes. So that's the other conversion we have to do, seconds to minutes. All right, hopefully everybody knows that. There's 60 seconds in 1 minute. So we have to use two things here in order to get from revolutions per second into degrees per minute. So let's go back to what we started with, 3.4 revolutions per 10 seconds. And the first thing we're going to work on is that conversion between revolutions to degrees. So I'm going to multiply. What are we canceling out? We need to get rid of the revolutions and end with degrees on the top. So I'm going to take 1 revolution as 360 degrees, and I'm going to make sure that I write it correctly so that I can see the units cancel. So that means that we're going to have 360 degrees on the top and that 1 revolution on the bottom so that I can have the revolution units cancel on the top and the bottom. The other thing we've got to convert is seconds to minutes. So I need to make sure that these seconds, which are in the denominator right now, cancel, which means I need a second in the numerator. So that second piece, 60 seconds in 1 minute, minute needs to go in the bottom because that's what we want. We want degrees per minute. So I'm going to cancel those units, revolutions, top and bottom, and then I see seconds cancel out here in the top and the bottom. And then we're just going to plug this all into our calculator and see what we get here. So when I do across the top, 3.4 times 360 times 60, we're going to end up with 7,344 degrees on the top. And then on the bottom, we're looking at I skipped ahead. 7,300, it's going to be 73,440 degrees over 10 minutes. And then we can simplify. So that is going to be 7,344 over 1 minute. Okay. Simplify with this worksheet. No decimals. Make sure you give me simplified fractions and show every step. All right, let's do one more and then we'll move on to the notes. So find number 12, it's down there at the bottom. 20 miles per hour, we want to turn that into inches per minute. So this is going to be a little bit longer than that last example just because there's a lot more conversions to think about. So we're starting with 20 miles per hour. I'm going to rewrite it like this. And we need to convert to inches per minute. So the first thing we need to worry about is miles to inches. Now, I don't know the direct conversion between miles and inches. I don't know how many inches are in a mile, but I do know how many feet are in a mile, and I know how many inches are in a foot. So this is going to take us a couple of conversions in order to get miles into inches. Unless you have miles to inches memorized, and that's impressive if you do. All right, so let's do this. First thing I want to do is convert miles to feet. So I'm going to have to expand my road map here. We're going to go miles to feet and then to inches. So if I'm trying to cancel miles out, I need a miles in the denominator. That means that 5,280 feet are going to go in my numerator, and that gives me 1 mile. All right, next from feet to inches. So I need to cancel feet, so I'm left with inches, which means there needs to be a foot in the denominator of my next conversion. So 12 inches is 1 foot. And then let's cross out the units that cancel. So feet are gone, miles are gone, and we're left with inches, which is what we wanted in the end. All right, the next thing we had to worry about was hours to minutes. So that was the last conversion. We can convert hours to minutes. Where are we trying to cancel though? We're trying to cancel hours, which means if hours is here in the denominator, we need hours in the numerator. I'm just going to erase this so we have more room here. Okay, so I know that there are 60 minutes in an hour, but 1 hour is also 60 minutes. All right, what cancels? Hour. And so check your final units. We have inches per minute. That's exactly what we wanted. So type all of this into a calculator and see what happens. Across the top, we have 20 times 5,280 times 12, all of that being divided by 60. So that is going to give us a final value of 21,120 inches per minute. Okay. So that's how you guys are going to finish 1 through 15 on this worksheet. And that's practice for dimensional analysis. Okay, so find your half-sheet handout that says Day 1 Examples. It should be white for you guys. And we're going to work through some of these example problems. So you guys are looking for the handout that looks like this. For you guys, it's white. But before we actually do these problems, there are 2 super important equations that you have to know for this unit, and that is it. So if you guys have these ones memorized, you're good to go. So let's talk about what a concentric circle is first, and then I'm going to give you guys the equations. So concentric circle systems means we're looking at circles that have the same center and are moving at the same angular velocity. So today we're just going to focus on a really simple system. All right, but imagine we've got our circle there. Okay, so think about it this way. Think about riding a merry-go-round. It's one of those things on a playground. It's actually really dangerous when you fly off of it. But on a merry-go-round, as it goes around in a circle, why does it feel like you are moving faster if you are the person sitting on the outside than if you are the person hanging on the inside? Why does it feel faster if you're the person on the outside? We're going to talk about that in this unit. So the real answer is that you are actually moving faster. Your linear velocity if you are the person sitting on the outside of a merry-go-round, is faster than the linear velocity of the person sitting on the inside. That means that in the same amount of time it takes for the merry-go-round to turn a specific angle, so let's say we start here, we're turning through this angle, I'll call it theta. Everything on the circle is going to turn through that angle at the same time. Okay, every piece of my pen is going to turn through that angle at the same time. But what happens is this person sitting on the outside has to travel a longer physical distance than the person sitting on the inside. The radius of this person on the inside is shorter, not the radius, sorry, the arc length of the person sitting on the inside is shorter than the arc length of the person sitting on the outside. So the person on the outside has to travel over a larger distance in the same amount of time as the person on the inside, because we're going to travel through the same angle at the same time. It's a little confusing. We've got a little while to get really solid on this concept. Okay, but what we have to know is this: in a concentric circle system, which is what we're focusing on today, something called the angular velocity is going to be the same everywhere. That means that every single point on this circle is going to turn through that angle at the same exact time. So in a concentric circle system, angular velocity is the same everywhere. Okay, one point you have to know about a concentric circle system. Point number 2, the linear velocity depends on the radius or the distance away from the center. Okay, so angular velocity is going to be the same everywhere. We're going to turn through the same angle at the same amount of time, but the linear velocity is going to depend on your distance from the center. Again, the person closer to the center, the person with the smaller distance from the center, has to travel less far than the person farther away. All right, I will clarify this on Monday, but let's talk about those important equations. So 2 important equations you have to know for this unit. Let's talk about what they mean, and then we're going to use them in the notes. So, first important equation, linear velocity. Let's label that. V is going to stand for linear velocity. Okay, what is linear velocity? Well, linear velocity is things like miles per hour, kilometers per hour, inches per minute. It is a measurable distance in linear terms over time. Omega is our angular velocity. That's going to be things like degrees per minute, radians per second, rotations per minute, revolutions per minute. And then lastly, that's our radius, or the distance from the center. So our linear velocity is equal to the angular velocity times the radius, or the distance from the center. And then the angular velocity is equal to its linear velocity times 1 over the radius. We could also write it as angular velocity is equal to linear velocity divided by r, or the distance from the center. Okay. So 2 super important equations, just make sure you have those memorized, and then we're actually going to apply them here. So find that half sheet of paper. Okay, let's give this a go. The one last thing you want to make sure always happens is anytime we are looking to find the linear velocity, angular velocity is always going to have to be in radians. Okay, you cannot use this equation if angular velocity is not in radians. So just make a note, it doesn't matter what the time is on the bottom, but the unit for angular velocity always needs to be radians per amount of time. Things aren't going to cancel correctly if we don't have it in radians. All right, so here we go. Examples. First one. We have a record that rotates at 33 1/3 revolutions per minute. Okay, 33 1/3 revolutions per minute. I'm going to mark that like that. First question. How many radians per minute is this? So we need to take revolutions per minute and just convert it into radians per minute. So let's do that. We did that on the first page. 33 1/3 revolutions per minute. I'm going to rewrite it like this. And we're trying to get it to radians per minute. So we've already got the minutes. I just need to turn the revolutions into radians. So what do I know about revolutions and radians? Well, I know that 2 pi radians is 1 full revolution. 2 pi radians is 360 degrees, 1 full revolution. So if I just do this math here across the top, we are going to get 66 2/3 pi radians, and then minutes are going to go on the bottom. The revolutions are what canceled. Okay, so 66 2/3 pi radians per minute. Please make a note. This is the angular velocity. Okay, the record is turning at 33 1/3 revolutions per minute. Revolutions per minute, also another way to measure angular velocity. So both of these values represent the angular velocity of this record. They're just in different units. All right, so part B says find the angular velocity of the needle when it's just starting the record. So about 14.5 centimeters from the center. Well, what do we know about angular velocity on a concentric circle system? We know that radius doesn't matter. The distance from the center doesn't matter when we're talking about the angular velocity. So I'm just going to make a note. This doesn't matter when we're talking about angular velocity. Doesn't matter. All right, so what is the angular velocity? Well, the angular velocity is either 33 1/3 revolutions per minute, or we can express it as 66 2/3 pi radians per minute. Unless I specify what units you need, either of those options are valid options for the angular velocity. Okay. The next problem, though, find the linear velocity of the needle. So with linear velocity, the distance from the center does matter. So let's write the equation of linear velocity. The equation for linear velocity is equal to the angular velocity times r, times the distance from the center. So let's fill in what we do know. So the first thing we need is the angular velocity. Now remember, anytime we're applying this equation, the angular velocity must always be in radians per minute, which means that between these two ways of expressing the angular velocity, we have to use the angular velocity given to us in radians per minute. So when I plug these angular velocities into this equation, we're going with the equation, or the angular velocity in radians per minute. Okay, so 66 2/3 pi radians per minute times the distance from the center, which is 14.5 centimeters. Okay, here is the trickiest part about this entire unit, and every year it's just something you've got to wrap your head around. In math related to linear and angular velocity, we call radians suppressed units. Okay, what that means is that we can express any distance from the center as its length or distance in units, like centimeters or feet or inches, but then we can always express it over 1 radian. That's what we mean by suppressed units. They're kind of like invisible units, those radians, when it comes to being with the distance from the center. So when I actually include those invisible units, we see that the radians cancel. That's where we get just the centimeters per minute and our linear velocity. All right, so when we do the math, this is 966 2/3 pi centimeters per minute. Okay, so again, distance from the center has the suppressed units, those radians. We can put any distance from the center over 1 radian so we can see the units cancel. All right, find the angular velocity of the center of the table. Well, if we're looking at this record, imagine you're sitting on the center of that record, and as the record is turning, we're looking for 2 things. So again, angular velocity is the same everywhere on a concentric circle system. So if our angular velocity was 66 2/3 pi radians per minute, 14.5 centimeters away from the center, as part B tells us, that means that it is also 66 2/3 pi radians per minute in the center of the circle as well. And our justification is that the angular velocity is the same everywhere on a concentric circle system. Okay, last piece for number 1. What's the linear velocity at the center of the circle? Well, again, imagine you're sitting on the center of this record. Now, the linear velocity is the actual physical distance that we have to travel to go from one part of our circle to the next. But if we're sitting at the center, we don't actually have to travel anywhere. Even if we're just turning, like imagine you're turning at the center, your physical distance isn't moving. You're just rotating, which is why you have angular velocity. But at the center of the table, our linear velocity is equal to 0. Now, mathematically justify, well, the equation for angular velocity or linear velocity is the angular velocity times the radius. We know that the angular velocity is 66 2/3 pi radians per minute. But what's the radius at the center of the circle? The radius is 0. Right? We are 0 units away from the center of the circle. That is why our linear velocity is 0. Okay. One more example, and then you guys are going to have the rest of the period to work on your homework. Okay. Last one, number 2, pinwheel problem. The tips of the spokes of a large pinwheel 1 foot from the center are rotating at 20 inches per second. Okay, great. Let's attempt to draw a pinwheel. It's like a little flower. Maybe. Okay, that's my pinwheel. Alright, so essentially, a pinwheel is just going to make a circle with the center where all of the spokes come into play and touch each other. Alright, this is a really big pinwheel though because the tips are 1 feet away from the center. Alright, and they are rotating at 20 inches per second. Now think about 20 inches per second. What kind of information is that? Inches per second is going to leave us with the linear velocity. Okay, so at the outside of the circle that this pinwheel makes, the linear velocity is 20 inches per second. Right, so always think about what information you're given before you start the problem. It's the best way to go. All right, what is the angular velocity at the tips of the spokes? That's the first thing we want to check. So the angular velocity at the tips of the spokes, we have an equation. Angular velocity is equal to linear velocity times 1 over the radius. Now we know the linear velocity is 20 inches per second. And then the radius here is 1 foot. Okay? So we're 1 foot away from the center when we're moving 20 inches per second. Okay, remember that those units of radian are suppressed units. So when we talk about or express the distance from the center, we're always going to put them over or under 1 radian. All right. Last thing is this. Angular velocity, we want it in radians per second. So right now, we have the seconds, but I need things in just radians, and the inches and the feet are not canceling out. So what do we need to cancel? I need to find ways to cancel inches and feet. So I know that 1 foot is 12 inches. And now we see our units cancel. Feet are gone, inches on the top and bottom are gone, and that's going to leave us with radians per second. All right, multiply everything across the top. We get 20 over 12, which is going to give us 5 radians every 3 seconds. That is our angular velocity for this pinwheel. Okay, so then what is the linear velocity at a point on the spokes 4 inches from the center? Well, linear velocity is the angular velocity times the distance from the center. We know that the angular velocity is 5 radians per 3 seconds. And then we're looking 4 inches from the center. So 4 inches, remember, that's distance from the center, so we're going to put it over 1 radian so we see the units cancel. And that is going to become 20 inches every 3 seconds. Okay, what is the linear velocity at the center of the pinwheel? So we're back to kind of what we talked about in D and E in problem number 1. Linear velocity at the center of the pinwheel. So we're sitting on the center of the pinwheel. Do we actually have an arc length to move through at the center? No. Another way to think about it is that the distance from the center is 0, and when we're calculating linear velocity, we have that equation, angular velocity times the radius or distance from the center. So it's just 0. Anytime we're sitting at the center of a concentric circle system, the linear velocity is 0. Okay, I'll make my justification that the radius at the center equals 0. All right, what is the angular velocity at the center of the pinwheel? So we're looking at a different value here, angular velocity. So what do we know about angular velocity in concentric circle systems? Well, we know that angular velocity is going to be the same everywhere. So what does that mean? Well, we know that the angular velocity was 5 radians per 3 seconds, so the angular velocity at the center is going to be the same, 5 radians every 3 seconds. How far from the center is a point on the spokes rotating at 10 inches per second? So this inches per second, 10 inches per second, that's the linear velocity. We want to know how far from the center. We are solving for the radius here. So our equation for linear velocity is angular velocity times the radius. So if I take that and I rearrange it, the distance we're solving for, distance from the center, is equal to the linear velocity divided by the angular velocity. So let's plug in what we know. Well, I know that the linear velocity here is 10 inches per second. Okay, 1 second. And then I know that our angular velocity is 5 radians every 3 seconds. So I'm going to make a really big and messy fraction there. And so what this actually comes out to be, if I want to write it a different way, 10 inches per 1 second, that's our linear velocity, times the reciprocal angular velocity, 3 seconds per 5 radians. Okay, and what happens is the seconds cancel. We're left with 6 inches per radian, because that's that unit that we see here. But remember that when it comes to distance from the center, radians are those suppressed units. So the answer is 6 inches. That means that 6 inches away from the center of our pinwheel, the linear velocity is 10 inches per second. Okay. All right, so your homework tonight is to finish all the problems on the back, and then and I will check that work on Monday. Have a good weekend, you guys. See you later.